Hey, welcome to the video. This is part of my series where I break down the core ideas behind databases and the systems we build on top of them. Today, we're tackling database isolation levels, what they actually protect you from, what they let through, and how to pick the right one. By the end, the 4 levels in the SQL-standard will feel obvious instead of intimidating. Let's get into it. Here's a scenario. 2 people hit buy on the last item in stock at the exact same moment. Both read the inventory, 10 items. Both subtract 1. Both write back, 9. You just sold 2 items, but your inventory only dropped by 1. One sale vanished. That's a concurrency anomaly. And the database setting that decides whether this can happen, and a whole family of similar bugs, is the isolation level. Isolation is the I in ACID. It controls what one transaction is allowed to see and do while other transactions are running at the same time. Get it wrong, and you get subtle, intermittent data corruption. So let's understand it properly. Quick foundation first. A transaction is a group of database operations treated as one unit. All of them succeed, or none of them do. ACID is the set of guarantees around that: atomicity, consistency, isolation, and durability. Isolation is the one that deals with concurrency. And here's the single most important idea in this whole topic, the core trade-off. Higher isolation prevents more anomalies, but it does so with more locking and more waiting, which reduces concurrency and hurts performance. Lower isolation gives you more throughput, but lets more anomalies slip through. There is no best isolation level. There's only the right one for your workload. Everything else in this video is just understanding what you're trading. Before the levels, you need the vocabulary of what can go wrong. There are 4 classic anomalies. A dirty read is reading data another transaction hasn't committed yet. Transaction A changes a price from 100 to 80, you read 80, and then it rolls back. You just saw a price that never really existed. A non-repeatable read is when you read the same row twice and get different answers. You check your balance, 1,000. Someone withdraws 200 and commits. You check again, 800. The row changed underneath you mid-transaction. A phantom read is about new rows appearing. You query all booked seats in row 5 and get 3. Someone books a 4th and commits. You run the same query again. Now there are 4. A row that wasn't there has materialized. And a lost update is our opening example. 2 transactions read, both write. One overwrites the other silently. Worth noting, lost updates can sneak in at any level if you do a read then write, without proper locking like select for update. Keep these 4 in mind, because the isolation levels are defined entirely by which of them they allow. How does a database actually enforce isolation? 2 broad mechanisms. The first is locking. Shared locks let many transactions read the same data at once, but block writes. Exclusive locks block everyone else, readers and writers, while one transaction modifies data. There are also range or gap locks, which lock not just existing rows but the gaps between them. That's how you stop phantom rows from being inserted. The second mechanism is MVCC, multi-version concurrency control, and it's how Postgres, MySQL's InnoDB, and Oracle work. Instead of locking readers out, the database keeps multiple versions of each row. A writer creates a new version rather than overwriting the old one. So each transaction reads from a consistent snapshot, and readers never block writers and writers never block readers. The cost is storing and eventually garbage collecting those old versions. Keep both in mind. The same isolation level can be implemented either way. Now the 4 levels, weakest to strongest. Read Uncommitted is the floor. It allows everything: dirty reads, non-repeatable reads, phantoms, lost updates. Barely any locking, so it's fast. You'd only reach for this where approximate is fine. A real-time analytics dashboard showing sales today that refreshes every few seconds. Reading a value that's 50,125 when the committed total is 50,100 doesn't change the decision, and you skip all the locking overhead. Read Committed is the first level most people should actually use, and it's the default in Postgres, Oracle, and SQL Server. The one guarantee it adds: you only ever read committed data. No dirty reads. It still allows non-repeatable reads and phantoms. This is the sweet spot for general web apps, browsing an e-commerce page, a social feed. If the laptop's price changes from a committed $9.99 to a committed $10.99 while you read the page, that's fine. You never saw a fake value, and you'll see the real current price at checkout. Repeatable read adds a stronger promise. Any row you've read won't change for the rest of your transaction. Read it twice, get the same value. It's the default in MySQL's InnoDB. In the strict SQL-standard, it still allows phantoms, though Postgres' implementation prevents those too. This is what you want for a financial report. You read the account balance. Someone commits a 5,000 change mid-report, but your transaction is pinned to its snapshot, so your balance and your transaction sum still agree. Internal consistency over absolute freshness. Serializable is the top. The guarantee is the strongest possible. Transactions behave as if they ran one at a time, in some order, never overlapping. No anomalies, period. Think a bank transfer checking a balance before debiting. At Serializable, two concurrent transfers can't both read the old balance and both succeed. The database either orders them or aborts one. It's enforced either with strict two-phase locking plus range locks, or with serializable snapshot isolation, which lets transactions run optimistically and aborts one if it detects a conflict that would break serializability. The price is more waiting and occasional retries. So how do you actually choose? Match the level to the shape of the contention. Two real cases make it click. Booking a specific movie seat, row 5, seat 12, is a discrete item. A row-level lock at Serializable works great. Two people can't grab the same seat, but different seats book in parallel, so concurrency stays fine. You either get your seat or you're told instantly it's taken. Now contrast buying a TV during a Black Friday rush. That's a single shared counter with thousands of transactions hammering it. Serializable there would create a brutal bottleneck. So you use Read Committed plus application logic, temporary reservations, queues, optimistic concurrency. The trade-off you accept: you might reach checkout and hit out of stock. That's the whole mental model. Discrete, low-contention rows can afford high isolation. Hot, shared counters need lower isolation plus app-level tricks. Pick the weakest level that still prevents the anomalies you actually can't tolerate.